So taking a look at these, we have three static scenarios, which means that everything is all balanced at this particular point, which means that we have the same amount of pressure from each side now that they're kind of like settled into their particular positions. Now, we do have the atmospheric pressure on both sides. So if we have the same exact atmospheric pressure on both sides, that's a non-factor in creating that differential. Now on this side over here, we have some water. And on this side over here, we have some kind of unknown fluid that has a density of 750 kilograms per meter cubed. And we're going to figure out what exactly that height is based on that density of that fluid. Now, what we need to do is we are going to use the formula pressure equals rho GH. And we're going to set up rho GH on each side of the manometer. So we have H2O on this side. We know the rho for water is 1,000 kilograms per meter cubed times our constant G times a height of 50 centimeters. On the other side, we have this substance with a density of 750 that also has the same G value, but it has an unknown H value. And it turns out that in these cases, because there's a G on both sides of the equation, we can go ahead and cancel those out. So we just have 50 times 1,000, which comes out to 50,000 on our left side, equals 750 times H. And then all you have to do from there is one simple algebraic step of dividing both sides by 750. And then our height comes out to 66.6 repeating. Let's go ahead and round that off. And since my original unit for the height was in centimeters, then my answer for my final height calculation is also going to be in centimeters as well. Okay, so that is our first calculation. And let's go ahead and move to our second one. Now, for our second calculation, we have a bit of a different scenario here. We have some kind of unknown fluid that's yellow over here, and then we have water filling in most of the tube on the bottom portion and then up on the right as well. Now, one main concept that you want to be aware of is that if the water is filling up sort of like a U or J shaped region like this, then if we kind of take a look at this imaginary line here, then we have the same amount of water on each end, and those pressures are going to balance each other out. So we really only need to consider these top regions that are applying pressure against each other, because these are going to be in equilibrium on the bottom, which means that if we're taking a look at our water on the top portion here, we have density of 1,000 kilograms over meters cubed. And then we're just going to consider our H value, because remember that G is going to drop out anyways. And let's see here. So we have 30, and then up to the top, there's an additional 20 centimeters there. So this one has 20 centimeters from here to here total, which means that there's 10 centimeters of fluid here, because there's 10 centimeters of empty space at the top of the tube. So we have a height of 10 centimeters of water above this little reference line over here. For our unknown fluid, we have a density that's unknown, and again, that G is going to drop out. And then we have 20 centimeters of that fluid above our reference line. So we have 10 times 1,000, we got 10,000 on this side, rho times 20, and then we can go ahead and divide both sides by 20, and then we have a value of 500 kilograms per meter cubed. And if you take a look at it conceptually, that makes sense because that is exactly half the density of water, water being 1,000, and then obviously 500 being exactly half of that. So, because it has half the density, half the amount of mass that it can pack into a certain amount of volume, we are going to need double the volume. That's why over here we have 20 centimeters worth of that fluid. And then on the water side, we only need 10 centimeters of that water to balance it out. All right, let's go ahead and slide to our last calculation. Now for our last one, we are going to solve for this unknown height right here, this little gap that's empty at the top of the left side of that manometer. And again, we have a similar situation where we can kind of create this little reference line here because we know that this amount of water over here is going to balance out that amount of water. And then these are the only two that are going to be the more significant portions that are applying pressure that we need to take a look at. So we have this unknown fluid over here that has a density of 680. So I guess it's basically not completely unknown. The density is 680. And then the height is 20 centimeters above that reference line. Now on the other side, we have water. And we do know the density of water is 1,000 as we've been using. And then we're looking for that unknown height. So if we take 680 times 20, we get 1,000. 13,600 equals 1,000 times h. We're then dividing by 1,000, and then we have an h value of 13.6 centimeters, which is not our answer, but it brings us pretty close. So we know that we have 13.6 centimeters of fluid going upwards, but that wasn't our main unknown variable. Our unknown is this gap here, and we know that this total distance from our reference line up to the top is 20. So then we're just going to go ahead and take 20 and subtract 13.6 for our final answer of 6.4 centimeters. And then that is going to be our final H value. So for these different problems, again, you're going to be utilizing the formula rho GH as the pressure that acts on each side of the manometer. And then we don't really need the G values because those are going to stay constant anyways. So we basically just have the density of the fluid on each side. And then you just want to be careful with picking what kinds of heights you're going to be plugging in. And then usually it's a couple quick algebra steps from there and you got your solution. So I hope that was helpful to you. Thank you for watching and listening.